Hello, I'm Sam, and this is my video for Lab 2, which covers free fall motion and the concept of drag. So for this lab, there's a couple formulas and stuff that you need to think about and take into account. The top left one I'm going to talk about last. I'm going to start with the one below that, which we talked about in the last lab, which is Newton's second law, which is force equals mass times acceleration, which is also force is the change of momentum over the change of time. With the force equals mass times acceleration, in the momentum principle, you can divide that by mass to get what is the velocity update formula, and then integrate that formula to get the formula you see on bottom, which is what's called the second parametric equation. It's also referred to as the position update formula with that velocity time added to it, but we don't need that because we're going to be starting from rest. The second one is the gravitational force equation, which really only matters when both of the masses are relatively large. Since we're using a smaller mass, today we can treat the force of gravity as if it is always 9.8 meters per second squared. And then lastly, we're going to be talking about drag, which is what you see there, and that is pretty much how much an object in free fall is slowed by the air resistance as it falls. So here is my video, here's a screenshot of my object falling. You can see I use the tracker app on my laptop to get the positions, and then here separately is just a video of the object itself. I chose a slice of ham that I dropped for my free fall object because I thought, because of its shape, kind of frisbee-like shape, that it would fall pretty slowly and would be affected a decent bit by drag. So I obviously put it in my glow script after tracking it. This is everything I changed in my code to make it accurate to what I did. My units are in millimeters, so that's not 514 meters, that's 514 millimeters. And the x-axis was not set to the bottom of the screen, it was set to the table. So it ends up falling from 514 millimeters to about negative 1500, not from 514 to 0. Here's my first position versus time graph. This is on the glow script code. It uses the numbers, which you'll see on the next, or in 2 slides from now. But that position versus time is exactly, the arc shape is exactly what you would expect in a position versus time graph, whether or not you're accounting for drag. Actually, if you are accounting for drag, which obviously our video does, it would plateau a little bit at the end, or not plateau, more so it would get, the derivative of the line would be less. So it would get steeper and steeper and then start to not get steep as quickly, which you kind of see, but not that clearly on this graph. So I don't think that the drag is affecting its motion very much. The velocity versus time looks pretty much constant. It's headed in the negative direction because it's going down. This is what you'd expect. You'd expect it to be increasing linearly, which is almost exactly what you see here, which once again means that the drag that is acting on it is not making much of a difference. So here we've got, with our numbers now, our graph. On the x-axis, you've got time. On the y-axis, you've got the y-axis of the falling thing, its position. The red line is what I marked on the tracker app. The blue line is what you would expect in perfect free fall without drag, which is why the blue line is so perfectly straight, and then the red line kind of staggers on and off of it. And then yellow is what I should have expected with drag based on everything I measured from it. And you can see that the yellow kind of gets higher and higher, starts to come off the Y position, which is what you would expect because drag is ultimately something slowing it down from what it would do in a vacuum. But for some reason, we didn't see that happen with our object. So what I expect happened here is that the ham, even though it had its frisbee shape, because it's flimsy, when I dropped it, it made more of a conical shape with the center lower than the rest, which would make it more aerodynamic and less affected by drag. So in the 1500 millimeters, which I mean is 5-ish feet, we didn't have enough time to watch it actually get affected by drag. We didn't have time to see the air resistance slow it down because we were looking at such a drop from such a small thing. Whereas if we had dropped our ham off of the top of a building, we would have seen that. So, I mean, that's kind of what I got from this.